where we are right now is section 6.2, trying to finish up basically our foundational skills of triangles. We've talked about right triangles and all their relationships. We took like a timeout in some senses of like the physics sense of triangles by going and talking about trig and all the trig functions and how you can play with the trig functions, manipulate trigs, form T-proofs and all that jazz. Trig equations about using the unit circle, but also our calculator's inverse trig. So we played a lot with trig itself, building off the right triangle. Now we're like, what about those non-right triangles? And all of that, in some senses, is kind of building up to this pre-physics section, 6.3, 6.4, 6.5. Just kind of giving you peeks at how trig can be applied. It's not necessarily that they're all going to be non-right triangles. We're still going to be working with right triangles in 6.3. So some of the relationships, some of the laws, some of the formulas might actually get easier, but there are variations of how to solve. One way would be a lot of geometry and a lot of just triangles the way they are, which would be having to use these sections. But then we're going to kind of be like, but can we kind of manipulate it like we've done with trig in order to do it an easier way? Anyway, that's all coming in 6.3, which we get to introduce after we finish this section. So you guys have homework out to ask me where you've gotten stuck after we finish our quick examples. And then we're good to go. Just remember Google Classroom submission tomorrow on this homework 6.2. But we're still a little ways out from the test. I think the test is probably end of next week, maybe beginning of the next week. So we still have some more time. It's actually probably the weekend after that. So coming back in here, I think yesterday, I just wanted to really quickly make sure we're good with plugging this guy in. With a square root, we should never have any issues as far as errors in your calculator. Remember, I'm doing a twofold. I'm teaching, but I'm also making sure you know how to use your resource, your tool, your calculator, yeah? It's this whole chapter. You're allowed to use it. Just a quick heads up with the formula. Like with the cosine formula, the one that we did yesterday, we had to use a cosine inverse to get to the angle. For this one, since it is kind of Pythagorean-ish in nature, we do have to throw in that square root at the end. So once again, just a way to be efficient with your time and with your resources is throwing in that square root at the beginning. The more that you can condense it all at once, hopefully the less you get lost, because sometimes a lot of you love to like add and then subtract and then multiply and have all these different decimals compounding. It's just a mess. So if you can become unafraid, if you can be more confident with your calculator, it should definitely be to your benefit. So then throwing in this expression to our calculator shouldn't be too bad as far as solving. I don't think you guys necessarily need me to throw this into this calculator. And I forgot I put mine back here to update some of your guys' operating systems. I think I double checked the two guys' calculators I fixed yesterday, or I should say updated. You might want to double check your alpha y equals now that you get that nifty new feature, and actually a lot more too, which would be nice. But when we throw this in, 6.2 squared plus 9.5 squared, are you guys coming up against any weird errors in your calculators as you're doing law of cosines stuff that you want to check in with me right now about? Any weird errors? Okay, I think we've fixed most things there. Just a quick reminder to watch out for those parentheses. And we talked about yesterday a quick reminder of where to find these minutes, right? Because we get to find them in our second apps menu of degrees and minutes, if they show up. They might show up here and there. But this one, I go ahead and get my B to B. Not sure if any of you guys did this work. I know we're kind of picking up in the middle of a problem. But once we get B to B 3.337, anybody back me up on that? Anybody do it yesterday? Or have it in your calculator today? I'll still wait. I'm just looking for a thumbs up from someone. But just keep an eye on your directions, because in this one it says to solve the entire triangle. And so my question is now, how do you proceed forward? Some of you have done homework and you've realized some of the directions are use whatever law works for you. Careful. But you still have to be within the confines of whatever law works. How would you guys proceed forward? What do you think? Now that you have side, 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 and an angle, I'm just curious, would you go forward with law of cosines or go forward with law of sines? What do you think? Okay, it depends on what you're comfortable with. I just heard both. I heard cosines from the back, and I heard two different law of sines from the front. Could you do law of sines? The answer is most definitely yes. Because can't you, what are we missing? Angles? Yeah, we're missing angles. You guys good? Yes, something wrong with the calculator.
got 9.
Ah, in a big old square.
Yeah, I do.
Let me see the whole thing. Oh, so you're just checking to see if I was right or wrong. Got it, backtrack that. So I have 6.2 squared plus 9.5 squared minus 2 I'm missing 2 parentheses, but it shouldn't make a big deal. It's 2 times 6.2 minus 9.5 times cosine 5. Am I in radian mode? I'm in radian mode. Sorry. You guys have heard me say before, maybe you haven't. Calculus is all radians, whereas now we're all in degrees. Thanks for checking it out. 9.94?
Yeah.
Good job, guys. Good job double checking, but as soon as you guys realize you have the same answer, it's not lining up with mine. Feel free just to get my attention instead of me having to enter in and figure out what's up. So then as we go ahead and plug and chug, we could do law of sines. I just want to do a quick warning with you on law of sines, because if we were to go looking, what's the dilemma as soon as I'm using law of sines to find an angle, guys? Do you remember? Has it been too long? Well, you have to use the whole thing. You have to get a few more, I don't remember where I rounded, yeah, get a few more decimals in there. That's one thing, just because I'm using a rounded answer. But to be honest, however we proceed forward, I think we're going to have to use this rounded answers in law of cosines or law of sines. So we're going to be stealing it. Let me show you a cool way to steal it in just a second. But I'm still curious of my original question. What's dangerous about using law of sines to find an angle? Yeah, the ambiguous case. Whenever you have to use sine inverse in section 6.1, you have to think of both. Remember the 2 pages, the sine inverse and the 180 minus sine inverse? And here's the tricky thing is this one's not ambiguous. This one is a definitive one, so you'd have to be careful that you choose the correct angle for the information that you've been given, because you know how long in this one, which is kind of awkward because angle B is like up here somewhere. Angle B would be 75/20. You know that this would have to be 6.2, and you know that this would need to be A, B, C. C would need to be 9.5. There's only one triangle that has an SAS. It's not an SSA, but when you go plugging into law of sines, it's like an SSA. Just something to be aware of. You'll probably be okay because we can't, I don't think we can fit an obtuse angle, at least not in a way that will have this 9.5 still be true, because we need 2 pretty long sides. We can't have one of those weird, awkward, squished sides that the obtuse angle forms. But anyway, I'm not saying you're wrong if you go to law of sines. It'd probably just be safer if you're finding an angle to be using law of cosines, unless it's an SSA, then you're kind of stuck no matter what, and law of sines is probably easier. So anyway, not saying you're wrong, just saying it'd be a little bit iffy. As far as law of sines isn't the best way to go looking for angles per se. Anyway, that's just something you guys be playing around in homework in the sense of finishing off these triangles, whether you do law of cosines the whole time or whether you go to law of sines. Just kind of be aware. I want you to realize that when you're doing sine inverse of angles, there is that ambiguous possibility. Okay, go ahead, Abby. Go ahead. Okay. So then as we finish off this problem, I don't think you guys need me to model that. That's more of a homework problem if you guys get stuck. What if you get thrown a word problem in homework? Could it be messy? Could be. Is this one messy if they give you a picture and if everything's all nice and clear and defined? No, not really. Because this one, if you guys look at it, even though you could spend a lot of time on the whole paragraph, if they give you a picture, check out what you've been given. And if they give you the actual triangle that you're going to be solving, it's not a huge deal just to go ahead and solve. But what made the word problem in 6.1 a lot harder than this one? You guys remember that one? It had an A, B, C, D. I think we already talked about it, right? The leaning tower of Pisa one? What made that one hard? problem. You should spend at least some time on it and some time correcting it. If it wasn't hard, man, I should start throwing hard word problems on tests. Yeah. Nope, I'm looking for an answer. Sure. I said this one should be pretty straightforward in solving because you're just finishing off the triangle that's already been started. I was just curious, in 6.1, that really nasty one, the ABCD one that should have taken a lot of time, or at least a lot of corrections, the Leaning Tower of Pisa, what made it harder? Aiden, what do you think?
There's like another little triangle on top of it.
Yeah. As soon as you have multiple triangles that you're working with, the Leaning Tower of Pisa one, you had like your Leaning Tower, which I think it depends on how you're looking at it, leaning this way. And then it was the right triangle that was outside. Yeah. And so you were given like not as much information, number one. So whenever you're given less information, it automatically gets harder. And whenever you're having to work with triangles on one side and on the other, it gets harder too. Kind of introducing when or how some of the word problems in 6.3 are going to get tricky. Because there's not just going to be one triangle involved. So anyway, just kind of a heads up. For word problems with one triangle, like, we gave you a few pieces, finish it off. That's super basic, super elementary, super fundamental. The ones that actually have you looking outside and having to consider other options or other factors, and especially if you haven't been given all the information, that's where that deeper thinking and that critical thinking really digs in or really applies if you allow it to. If you just see something that's a little bit harder and you're like, meh, well, I guess you're just going to stay on the elementary level, which is kind of sad. As we're finishing off section 6.2, we have this area formula. And I show it every year, and I label it every year, and I say like, hey, this S guy is not in your original ABC triangle with let's see, an A and a B and a C. It's not your normal ABC triangle. That's the ABC. Those are three sides. But every year, even though theoretically kids write this formula down and they even like get a name for it, it's called a semi-perimeter, I still get when we grade homework, who's the S? So the S, it doesn't make sense. If you don't write this page down, if you don't connect the idea, he's not going to make sense. Because you're used to triangles at this point, ABC, angles, ABC sides. You're going to know who the ABC is, but you're going to get totally messed up if you just start ignoring the S or not paying attention to who he is. He's the semi-perimeter, semicircle, half a circle. Semi-perimeter, half a perimeter. And how do we find a perimeter of any geometric shape? It's as easy as that. Add all the sides. Now, depending on your semi-perimeter, as you guys are writing this down, I'm going to pull up my calculator because I'm going to show you the nifty thing I kind of alluded to a second ago. Let me see if this can still be able to be seen. There's something cool that your calculator can do that I haven't really shown you too much this year, and it's really important for calc as far as for those calculator problems. It's not super important if you're in the home screen, but if you're in the graph, man, it gets super helpful. Because there comes a time where you're going to need to find maybe like intersections or zeros or maximums or minimums and then plug them into something else. And if you ever have to take something with nasty decimals from here and plug it in, it would be so much easier if I could copy and paste from the graph. But the problem is if I was to do something like get this intersection with number 5, the only way right now that you guys know to copy and paste is from the home screen, like going up and selecting and then having it copied. If you were to try something like that, second curve, sorry, I did the wrong one, I meant to do 0. There he is. To go back up. First of all, this scrolling thing can get super tedious and super annoying. It's super nice if you guys remember that we can actually want to just type a button and be like, there's 1, and then I guess 5 would be on the other side. It's super cool if we know some of those shortcuts that we wouldn't really know otherwise. Now this one is a nice 0, it's a 3. But if I was to do, let's see, what's something that would make this a bit nastier? Oh, there you go. Let's do something like 15. Let's do 15 minus 6. I should have done insert because that's what makes it nicer in our calculator too. Sure, that'll make it gross. Okay. So if I go to do my 0 on this one, I could just type 1, I guess. I could just type 3. Okay, I have a nasty decimal. What if I need to plug that in? What if I need to apply it to something else? Let me show you on the graph and then show you how it can help you kind of in this problem as well. The main application I'm about to show you is how can you copy and paste from the graph. If you have something that you just found with one of your really snazzy features like max or min or intersect or zero, you can quit out of that graph, just second mode, you have to quit, and right away you have to hit what's called the STO button. We didn't have to use it in our graphing calculator handbook earlier this year. We didn't have to. It was in there, maybe you saw it, maybe you didn't. But there's going to be a lot of times, especially in calculus, where we want to steal numbers from that graph, or even maybe from a table, but a graph specifically, and we want to stow it. Anytime we hit the letter A now, we can plug it into whatever we want, and we can solve and see what it is. We could even do what's known as function notation, telling our calculator to go look at the graph and the equation I've already plugged in, and tell it to put in that A, which it should be 0, because that is the 0 of the function. It's really snazzy if you have big old long decimals to start calling them by certain variables signifying that constant, because it'll make life easy. Why am I showing you that? Well, number one, I'm showing you what the stow button is most useful for. It's for copying and pasting yucky numbers out of graphs. But we can use it for the semi-primitive. Because for instance, this one, can't we use our nifty fraction feature to say, okay, cool, I want to go ahead and do 43, 53, and 72, the semi-perimeter of that guy. And then the cool thing is we could literally, in our calculator, we could make him, now I know it's not a horrible number, it's 84, what's the big deal? I know you could type it over and over again. We're just teaching you this cool feature in your calculator that will be useful later on. We could stow him as an S, and then from now on we could use it, meaning we could take the square root of, we could go grab that S, and then we could do, hey, and then it's going to be S minus our A, which is 43. Now I know some of you are like, once again, this isn't saving me a lot of time. Well, to be honest, I'm just teaching you something that will save you a lot of time in the future. But you could also do it with the 53, and then you could also do it with the 72. Oops, that's an L. That's not where it went. Alpha S. There we go. And then we can do that at 72. Anyway, you have to use that very same semi-perimeter every single time. You could have typed in 84, you would have had the exact same answer. As long as we typed it in right, minus 43, minus 53, minus 72. But if you don't realize who the semi-perimeter is, this formula is not going to work. And you might be like, well, what's the big deal of this formula? Remember, once again, you have a nasty triangle that is not right, whose area formula from earlier is so easy if only you knew the heights. It's not a right triangle, I don't know the height. So the only way to solve this without Heron's formula is P.S. Heron's or Heron's, I forget what's his actual name of origin, the original one. It goes both ways. I think he was from Alexandria. Anyway, he made a math book that showed up in a math book. A lot of these formulas are named for the guy who first wrote it down. Random information, there you go. But anyway, he didn't come up with the formula, but he figured it out, or he found it and put it in his math textbook. But we would have had to have figured out our angle, and from our angle, we would have had to use SOHCAHTOA, and it would have been a whole big mess. Has anybody backed me up on the 1,131 point? Thanks, Nathan. So that would be my final area without having to do law of cosines to find an angle, to do my sine, to figure out the trig, to figure out the altitude. No one wants to do that. It's a lot easier just to use this nice, sweet, let's just use the sides that we've been given. With that, let me go ahead and give you guys a chance to let me know where you're getting stuck in homework, if you've gotten stuck yet. Are there any places, because we're at the end of this too, any directions or any sections where you're like, this is weird, this is random? Nathan?
Going back to the ends, can you use that whenever they ask you to find the area?
Whenever they ask you to find the area, if you've been given 3 sides, so even in section 6.1, if you use law of sines to find a third side, use here. Or you could use here. I'm not sure if it really saves you time. But yeah, anytime you have 3 sides of a triangle, you can always use that for area, which is kind of neat. Sorry, back to homework. Has anybody gotten stuck?
25.
I was waiting on that one. I was waiting for this picture right here. If you guys haven't started homework, if I were you, add in one more example before we switch to section 6.3, because a lot of you aren't going to like the parallelogram section. Why would I give you a parallelogram problem if we're talking about triangles? Because it's composed of triangles, right? So, Justin, I gave you 25?
Yep.
Nice. So we're going to do 26. 25's an odd in the back of the book. You guys could totally just do that and then check out CalcChat. I just want to make sure you have the idea of it. So we have this parallelogram, dude. And they've given us some lengths of diagonals, right? And this one, they've given us in number 26, which theoretically should be a bit harder. They've given us two sides like your 25, and they've just given us a different angle. They've given us phi instead of theta. Man, I remember that one. I forgot that one. Anyway, so if we were to label this guy, we would have him being 25. We would have him being 35. Guys, what do we know about parallelograms? What can I label the opposite sides as? Yeah, the exact same thing. They're going to be congruent. Parallelograms are like rectangles in that they have congruent opposite sides, just they don't have right angles, right? I guess a rectangle is a parallelogram because both the sides are parallel. It's just a special one that's at a right angle. This one is not at a right angle. How do I know that? Because phi is 120. Which, does that make sense with this picture, the way it's drawn? For that angle to be 120. It's hard to know, right? Until I get my little nifty right angle out and say, does it make sense that that is 120? Yeah. I mean, maybe. It looks kind of more like 100, or maybe a 95. Like it's almost a right angle. They had to give you a generic parallelogram. This isn't the exact picture for all these different pieces of information, okay? Like in this one, if theta was 45, does that look like 45 to you? No, this would be way more squished. Just be aware. Be aware. They gave you a general one. They gave you a generic one. Okay, so we know that phi is 120. What are we supposed to be solving for? This guy. Ooh, who's the opposite side of 120? And then this guy, who's the opposite side of, do you guys see there are really two different triangles here? Here's one. 25, 35, and 120. Can I solve for C pretty easily? Yeah. Using, what do you guys think if it's a sine angle side? Law of sines or law of cosines? Cosines, because sines needs more than one angle to make everything nice. So law of cosines would be way easier, and I would have, let's see, C squared equals A squared plus B squared minus 2AB cosine of the opposite angle, which is 120, and then hopefully by now we realize we're square rooting, yeah? To get that side. Okay, I could get C pretty easily. The question is, how do I get D? I have two sides, but what's over them? I'm just typing in the 25 squared plus 35 squared to have an answer. Even though I guess it's an even, so you guys wouldn't even really know if it's right or wrong. I'm making sure I'm in degree though this time. Right. Angle. I can't go searching for D until I know I have side. I don't have the third side, and I don't have the angle. There must be some geometric way parallelograms. Sides are parallel. There must be some sort of property that I can use to get that. I'm going to go ahead and write down C real quick because we found it to be 52.202. What do you see is weight? You were saying it. What do you see?
120.
What about 120? No, not the same angle, but you're close. With parallel lines, if I have a transversal, alternate interior angles are congruent. So if this one's 120, then this one is also 120. But what would that one be? 60, because it's going to be supplementary. Alternate interior angles are congruent, and so the other guy would need to add up to 180, so there's a little bit of geometry involved. Nikki, what's up, kid? while I was training. Well, long story short, yes, there's not going to be a formula sheet for this one, and there's not going to be a formula card for this one. Or if there is, believe me, there's harder stuff coming. I would make you memorize 6-1, 6-2. So 6-3 is a beast, so I might let you have a formula card on everything to do with vectors, but I won't let the law of cosines, law of sines be on. Yeah. But that's also why yesterday I was trying to be like, there are 6 formulas. There's really just 2 formulas, and even really just 1 formula. So there are tricks to memorizing where you don't have to memorize as many as it looks like. But yeah, the 2 area formulas, law of sines, and then enough of law of cosines to be able to do it. But the nice thing is, for the rest of the chapter, that's all you need. Besides knowing how to use your calculator. Oh, so we have theta. And once we have theta, why am I putting my marker down even though we haven't done d yet? How would I find d? Law of sines. I mean, I guess you could. I was thinking I'd copy and paste this and just change it and say, well, it's still 25 squared and 35 squared and 2 and 25 and 35, but what's my opposite angle now? Yeah, I'm going to go steal that exact same thing I just typed and just do it all over again, but instead of putting 120, I'm going to put 60. And I'm going to end up with my final d of 31.22. It's just a side angle side. I would use law of cosines again. But Justin, I think that pretty much gets us there, yeah. So just remember the 2 relationships for homework, especially the relationship between your theta and your phi is going to be their supplementary due to this being a parallelogram and these being parallel lines. Is that good? How many do I give you in that section, Nathan, since you're looking at it? Yeah. Just 25? It's up to you whether you want to do the generic one or whether you want to do a specific one that has it much more realistic with the 45. So I want a quick picture of it. It doesn't need to be a huge one. But my advice, yeah, still draw it, because how are you going to think? I don't know. I wouldn't be able to process that information unless I was able to see it. And it's part of writing down the given information. But I don't think I'd do the generic. I think I would do one that makes way more sense for a 45 degree. Or was there any place else besides parallelogram was the one I was most worried about? You guys understanding. Is there anything else, though, that you guys got stuck on? Going once, going twice? Sold. All right. I told you guys we were going to be introducing 6.3. So at this point, I need you guys focused on in because the beginning of 6.3 at least gives us a beginning. Well, the introduction is 6.3. Hopefully at least gives us some motivation for what's to come. Remember, beginning of chapter 6, before we covered any law, I said 6.3 is pre-physics. Not just pre-calculus, but pre-physics. Physics, there is like non-calculus-based physics, and there's calculus-based physics. To be honest, once you've learned calculus, the calculus-based is easier because you understand more of what's going on and why the formulas are what they are. But the non-calculus-based physics is still rigorous. It's still tricky. You just have lots of formulas to have like on a sheet of paper and to try to use. But in section 6.3, what is this guy that's coming? What? Wait, what? Who is 6.3? How is this physics? Have you guys ever heard the term vector before? Do you know how to fill in the blanks yet? It kind of has to do with trajectory. That's good. Kind of has to do with trajectory. You just saw some pictures of roller coasters. New section. You just saw some pictures with roller coasters and roller coasters that had forces acting on the people in the car at different points. There's a lot of math. There's a lot of restrictions and guidelines that goes into designing a roller coaster because you kind of have to keep people safe even though you want them to totally freak out. No one knows how to fill in these two blanks, really? Direction and magnitude? How'd you know that? Oh, from... That's funny. To inspire us just a little bit. Most of you should have seen or at least heard the word vector before.
I'm applying for a new film loan by the name of Vector. It's a mathematical term. Quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new website. Hurrah-a-thon! Oh yes! Finest live piranhas ever seen before. Now you have my invention. You want a demonstration? Oh, ah! It's difficult sometimes to get my balance.
Okay, so how do we fill it in? Direction and... Oh, yeah. It's coming, it's coming, it's coming. Just wait for it. There you go. Where have you heard the word magnitude before? Come on, you live in California. Earthquakes. There you go. Earthquakes. Earthquakes. What is the magnitude measure of an earthquake? How strong it is, yeah, basically. That's a good way of putting it. How strong it is. Magnitude. We're going to talk a little bit more about it in future pages. Basically, I'm going to call it the how muchness. You're like, really? Well, here's the problem. How strong indicates some sort of force. So then if I just say how strong, you're like, oh, okay, all vectors have to be forces. Problem is, vectors can just be lengths that are in a certain direction. They can also be speeds. They can be how fast in a certain direction. They can be how much work, like how many joules in a certain direction. Vectors can be used for all sorts of different quantities. So I can't just say how strong. But the magnitude is how much there is, the greatness of it. Maybe the greatness is a better way of putting it. How about direction? Yeah, I know. You're like, well, I don't get it. It could also be like northeast or southwest, or it could be, okay. So direction, wait a minute, you can have all sorts of different directions. I think that has something to do with an angle. So that's like a, okay, can we put this in? This is like a length, magnitude. The length of a vector is going to be how much there is of it, which is weird because you're like, okay, wait a minute, you're going to make something a certain length to indicate how fast it's going, or make something a certain length to show how much force there is? That's weird. And then direction, we're going to be dealing with angles. Now let me show you a vector, and I want you to think about all of your geometry prior training and what's weird about this definition with this picture of a vector. Is there anything weird about it? It's a ray. But up there it says it's a segment. Hold on. Segments stop and rays keep. So here's the problem. This is not a ray. It looks like it, but it's not. There's actually a point at the beginning and there's a point at the end. The arrow is not saying go on forever. The arrow is saying it's headed in this direction. Meaning, the arrow could very well sometimes be this way instead, and then it'd be heading same angle but different direction. So the arrow in a vector, the first most important thing you need to know, it doesn't mean forever. It doesn't mean forever. The length has a meaning. The magnitude has a meaning. So there is a set length of this vector. There is a set length of the vector. That length is what we call the magnitude. We have some snazzy notation that we're going to bring in, but for right now, the length, it stops right there. The length is known as the magnitude. Out here, we can call this the terminal point. Terminal, ending, terminate, right? the terminal point, and then over here we have the initial point. It's kind of similar to an angle with an initial side and a terminal side. A vector has an initial point and a terminal point, and it turns at some sort of angle. Now, it kind of depends. Sometimes you're going to be measuring, ooh, I don't know what that is. Sometimes you're going to be measuring from our normal, oh, hey, directed line segment. You guys don't need to write that down. It is a directed line segment, so it's a line segment with a direction. We normally in math always measure standard position of angles from the positive x-axis, but to be honest, in GPS we already kind of talked about how some people measure from north, and that's called the compass bearing. Or you could even say something like southeast at a certain angle, and it could be somewhere different. So right now we'll say that's how we're going to measure all our angles, or at least that's what we're used to, but that might change just a little bit. But let me also put down here vector v. Now here's a weird thing. Vectors, we're going to always put arrows over. You can put a double-sided arrow if you want. I did put it up here with a little normal little arrow. But to be honest, that kind of makes me think geometry and rays, and I kind of want to separate you from that. So then I am kind of lazy. I just did a single little arrow with one little tail. Number one, it looks a little more technical. Number two, it's very different than a geometric ray. And number three, well, it's faster to write. But either way, the book is never going to show this little arrow though, and that's weird because the book is able to put things in bold. The problem is I don't want you writing in bold. So anytime we see a bold letter, you're just going to be putting an arrow on top. The book is going to be like, hey, bold letter, it's a vector. We're going to be like, okay, well, we can't do that. Okay, cool. We'll put an arrow on top. No, don't just make it a dark letter. Well, then how do I know that someone's not just random? No, put a vector arrow on top. That's like a handwritten way of doing it, handwritten versus typed. But with this vector, we can call it not just vector lowercase letter, but we can call it vector PQ, where P is the initial point and Q is the ending point. It has nothing to do with alphabetical order. It has everything to do with where it starts and where it ends. It has everything to do with where it starts and where it ends. Now, in getting to this page, I did do a couple things. I breezed past a couple pages having to do with roller coasters. Here's one I just stole off Google a couple years ago that kind of shows vectors, but if you notice, they're saying force, and they're labeling it with forces: apparent weight, gravity, actual weight, and acceleration, force, etc. And they're showing these arrows, but this is actually a very imprecise picture. It's a very just basic picture of like, oh, hey, look, gravity's always going, not gravity, where's gravity? Blue. Gravity's always pulling down, pulling down, pulling down, but apparent weight is against the track, against the track, against the track. Like if you were stepping on a mouse right now, your gravity would be against, or I should say your apparent weight would be against the track. But then you also have this acceleration force that's happening as a result of you being in the car. Anyway, this one's okay. It gives you an idea, but this one is way better because this one says, okay, we can see in the car these things working at different angles, but off to the side, if you realize, they've actually taken these separate vectors and they've tried to combine them to figure out the overall effect. Can you guys tell? I mean, this one's gravity, right? Can you guys tell which of the blue or the red, which one seems to stand for the overall effect? What do you think, the norm or the net? Have you ever heard of net profit? Like net means all together, the resultant. The net is how we, or what happens when we put everything together. Because even though it's helpful to some degree to know different forces acting on a certain object, it's much more helpful to be able to put them together. And so we're going to see tomorrow, how do we take vectors, right now I'm just going to do color coding, and how do we make or add or figure out overall net result. Well, if you guys notice, that's an oblique triangle, that's an oblique triangle, that's an oblique triangle. Oh, that's just like a plus because it's in the same angle. But these triangles that we've kind of been building up all of our knowledge for, taking a quick long side in trigonometry and how we can solve trig and deal with trig in our calculators and inverse trig, we're now coming to an actual practical application with vector and vector diagrams is what these are called. To take lots of forces and put them together and say, what's the overall effect? Bye guys, I'll see you later. We're going to be playing with vector diagrams tomorrow. bring your calculators up. Make sure you know how to do this. Vicky, what's up, kid? Yeah.